go over a very subtle point, but it's important if you want to understand the problem of the rod very well to get this point clear. So first, let's go over the general view that we talked about before. You have here the rod, it's moving with a velocity to the right, and these rails are fixed, and the rod is just sliding on the rails. And we showed that there's a charge accumulation on the top and the bottom of the rod, and that static charge makes an electric field in the wires, in the fixed wires, which makes a force on the charges, and that's what makes the current move in the wires. But if you take integration of the static electric field dotted into element of length over a closed loop, F static over Q is E static. If you take integration of E static dot dr over a closed loop, you always get zero, because the static electric field, it's a non-conservative electric field. The electric field due to static charges, it doesn't have a closed loop integral. We discussed this before many times. So even when we come to calculate now the work done on a charge as it goes around the complete loop, as long as it's going around the complete loop, the work due to the contribution due to the static, the conservative electric field is going to be zero. So we don't need to consider this when we talk about the work. Okay, so the following arguments are taken from this book, and they are the one that's the place where I got the reference where I got this material from. So we want to calculate the work per unit charge. The definition of the work, it's integration of F dot ds around the closed path divided by the charge. But the thing is, when you get the work, you need to get the work for the particle. You need to integrate over the actual path that the particle is moving on. So if you want to get the work on the charge, you have to look exactly where is this charge moving in space and integrate over that path. It's unlike the EMF. We'll make a comparison between the work and the EMF in the last slide, but if you want to get the work, you need to first identify what's the actual path that the charge is moving on. So let's follow the path of the charge as it moves. This is that horizontal rod that's moving with a velocity v wire. I just put the rod here at different points in time so that you can, I zoomed into the problem a bit and put the rod at different points in time. So this is at time t1, the charge and negative charge starts out here, and then at time t2 the charge reaches this point, and then it reaches this point, and so on. The charge moves on a diagonal. Why? Because the rod itself is moving to the right with a velocity v wire, but the charge is moving relative to the rod with a drift speed, v drift. This is exactly the same as, for instance, if you're moving on a boat in a river. So the velocity of the boat is v wire, it's moving to the right, the whole boat is moving to the right, but then you're moving relative to the boat downwards with a certain speed. Let's say you're walking on the boat downwards. So you have the boat itself is moving with a certain velocity relative to the fixed earth, but you're moving relative to the boat downwards. So the net velocity, if you look someone sitting on the outside fixed to the earth, he will see you actually moving in a diagonal path. So this is the path that the charge moves on when it goes along the rod, and then when it goes onto the fixed part of the circuit, this rod is fixed. It just moves with the drift velocity. There's no motion of the rod anymore, so it just moves with the regular drift velocity. And then it goes back here to complete the whole path. So this is the path that we have to integrate over if you want to get the work. Okay, so what other forces then are there? We know that the static electric field doesn't contribute to the work, because when you integrate that over a closed loop, you get zero. But what other forces could be acting then? So there's the pull force. Someone has to pull on this rod to the right to make it move with a certain velocity. If you don't pull on the rod will just slow down and stop. Because when you have a current in this circuit, a current in the rod, there's a force on the rod to the left. IL cross B to the left. And so if you stop pulling on the rod will just stop. It'll stop eventually. So to keep this rod moving with a constant speed, you have to actually pull it to the right. For instance, hold it with your hand and move it to the right. So that's what F pull is. And F mag is the force, the magnetic force on the charge. So the charge has a magnetic force Q V cross B. V is this way and B is into the page. So V cross B is actually this way, but since the charge is negative, then the force is opposite, so it's in this way. But it's perpendicular to the path that the charge is moving on, so it doesn't do any work. And we know that the magnetic force doesn't do any work, right? We've said this before, it can never do any work, the magnetic force. And when the charge is moving on the fixed part of the wire, also the speed is, in this case, V drift, but also the magnetic force is perpendicular to the wire, because V drift cross B is down and the charge is negative. So the force actually is up like this. It's perpendicular to the path. So along the whole path, the magnetic force does no work on the charge. So it's F pull that's the one that's responsible then for doing the work, and we'll see how this works in a bit. So if you want to apply Newton's laws for the horizontal direction, remember the speed of the rod is constant, so there's no acceleration. So that means the sum of the forces should be zero. So that means F pull, which is acting to the right, should equal to the component of the magnetic force to the left. The component of magnetic force to the left is F mag cosine of this angle. Now this angle is just 90 minus theta. So it's F mag cosine 90 minus theta. Because this angle theta plus this angle should be 90 degrees. Cosine 90 minus theta is sine theta, and so you get F mag sine theta. The magnetic force is QVB, because the angle between V and B is 90 degrees, so you don't get any sine 90 is 1. So you get QVB sine theta. So this is what F pull is. Okay. Now, if you want to calculate the work for this part, which is the only part that contributes to the work, no other part contributes, you get the component of the force in the direction of motion. This is the force that's going to be responsible for the work. So let's get its component in the direction of motion, in this direction. The component in this direction is F pull cosine theta. So that's the component of the force. And then you multiply by the distance, the actual distance that the charge has moved. The charge has moved from here to here. So this distance, we call it h. So it's the force, component of the force in the direction of motion times the distance. Okay, so the rest is just basically simple math. Sine theta, if you look at this big triangle here, sine theta is L over h. So that means h is L over sine theta. I can replace here h by L over sine theta. So that's one thing. Now, let's see, we have F pull. We showed when we applied Newton's law, we showed that F pull is QVB sine theta. And if you look at cosine theta from this triangle also, the distance that the bar has moved from here to here is how much? Remember, the bar is moving with a velocity v wire. So in an amount of time delta t, it moves a distance v wire delta t. So this whole distance is v wire delta t. So if you want to get cosine theta, it's the adjacent. The adjacent is v wire delta t over the hypotenuse, which is h. So it's v wire delta t over h. So substitute the cosine with this, the green part. Substitute F pull by the red part. The sine theta will cancel with the sine theta. You just get QVB. And so now we're ready to continue. So this is what we had for the work. Now, if you look at the speed of the charge as it's moving along this diagonal path, the speed of the charge is v. It's the resultant speed. That's the speed of the charge on the diagonal path. And how much distance has it moved? H. And how much time has it taken to go from here to here? Delta t. So that means the speed should equal to the distance over the time. That means v delta t over h equal to 1. There's v, there's delta t, there's h. When you multiply those things by each other like this, you get 1. So we can take them away. So what's left is then, if I want the work per unit charge, when you divide by q, what's left is BLV wire. Like almost like magic. If you get the potential difference across this rod, we showed it's BLV wire. The EMF, when you get it using the flux rule, it's BLV wire. If you get the EMF using the V cross B rule, it's BLV wire. If you get the work per unit charge, taking into consideration the actual path that the charge moves on, you get BLV wire. So everything works out fine. So to summarize, and this is important to illustrate what the difference between the EMF is and the work per unit charge. Although it turned out that they are equal, but they are very different things, because the EMF, even though the formula looks exactly the same, it's the integration of F dot ds over Q, but the thing is, what's the path that you're integrating over? When you get the EMF, you're integrating over the instantaneous path of the circuit that encloses the area, which is this rectangular path. Just take if you want the EMF at a certain point in time, take a snapshot of this circuit at that time, and that's what the path that you have to integrate over. That's the definition of what the EMF is. But if you're getting the work per unit charge, the actual work, you have to integrate over the actual path that the charge moves on. That's the definition of work. So you have to integrate over this diagonal path, and then this path, and then this. So this is the path that you integrate over when you get the work. So they are completely different paths. Okay? Now, and when you get the EMF, F pull is to the right. It's the force you're pulling the rod to the right with. It doesn't contribute to the EMF because it's perpendicular to the path that we're integrating over. The path is here, the ds vectors are here, so the angle is 90 degrees. So this doesn't contribute to the EMF when you calculate the EMF. But when you calculate the work, it's actually the component of F pull along the direction of the motion which is contributing to the work, which is resulting in the work. And F mag does no work at all since it's perpendicular to the path. So these are very subtle points. If you don't get them, we can always discuss them in the office. But it's important for you to think about them a bit, and so everything can be clear. And remember that this circuit is the same as this one. I zoomed in a bit, but it's exactly the same circuit. I put the rod here at different points in time to see how it moves and see how the charge moves in the rod, but it's exactly the same as this rod and these wires.